In this lesson, we're going to discuss a brief introduction to exponential functions. An exponential function is defined as f of x equals ab to the exponent x, where b is the base of the exponential expression and a is the vertical intercept. The shape and direction of the graph depends on the base of the exponential expression. If the base is greater than 1, then the function is going to be increasing, and b is then called the growth factor. If b is between 0 and 1, meaning it's a proper fraction, then the function is decreasing and b is called the decay factor. Let's determine whether the given equation is linear or exponential and if the graph will be increasing or decreasing. So in our first graph, f of x equals 0.98 to the x. We see that x is in the exponent position, so that makes it an exponential expression. Okay, so this entire expression here is exponential. Since 0.98 is between 0 and 1, our function will be decreasing. G of x equals 0.77 times x is going to be linear because we're multiplying x instead of raising it as an exponent. Since my slope here, 0.77, is positive, we have a linear increasing function. H of x equals 7 halves to the x. 7 halves is going to be greater than 1. X is in the exponent position, so it's exponential, and we're going to be increasing. And lastly, we have j of x equals negative 7 halves times x. So again, we see that we're multiplying the x, not raising it as an exponent, so that makes this a linear function. And since my slope is negative, it's decreasing. Take a look at the graphs for f of x equals 2 to the x and g of x equals 10 to the x on the interval of negative 5 to 5 and negative 5 to 50. What do you notice about the similarities and differences of the two graphs? Okay, so let's start by looking at the tables. So I'm going to type in 2 to the x and then type in 10 to the x. So in f of x, I have 2 as my base, and in g of x, I have 10 as my base. So before even looking at the tables, you should expect our g of x function to increase at a faster rate since our exponent is being put on a base that is a larger number. Let's take a look at the table, and we can see that as x is increasing, both f and g are increasing since they have growth factors. That means that they have bases that are greater than 1, but we see that g of x increases at a much faster rate like we expected because our base here is 10. I'm going to go to window and type in the window that was given to us. So we had negative 5 to 5. We're going to count that by 1. And then we had negative 5 to 50. And we're going to count that by 5s. So there's my 2 to the x. And there's 10 to the x. So again, we could also see graphically how the 10 to the x function is going to increase much faster. So we notice that they both have the same shape because they're both increasing exponential functions. We notice that neither one of those functions are actually going to go below the x-axis. There's actually a horizontal asymptote at the x-axis. So that means that there's a line that we're never going to go below. That's what an asymptote is. We can also see that looking at the table. You see those y values are getting smaller for the smaller x values, but they're never actually going below 0. Let's take a look at this application. 4 milliliters of a drug is injected into a patient's bloodstream. After 1 hour, half of the original amount remains in the bloodstream. For each succeeding hour, half of the amount present in the previous hour remains in the bloodstream. Write an equation for the amount of drug in milliliters remaining in the bloodstream, A of t hours since the injection. So let's start by just looking at a table and seeing what's happening here every hour. So t is my hours since the injection, and A of t is the amount of the drug that's remaining. So I know we started off with 4 mLs at t equals 0, so that's when the patient gets the injection. At 1 hour, there should be half the amount remaining, so there should be 2 mLs remaining in the bloodstream. After 2 hours, there should be half of the previous, so now that's 1 ml left in the bloodstream. After 3 hours, half of what was left at 2 hours, so that's half of an ml. After 4 hours, half of the original, half of the previous amount, so that would be 1/4 of a milliliter left. So we notice that each hour we're taking 1/2 of the previous hour's value. So if we're going to start off with our form, A of t equals AB to the t, remember A is the vertical intercept. The vertical intercept, regardless of what type of function we're looking at, is when the input is 0 and the output is a number. So I know my vertical intercept here is going to be 4. A is equal to 4 here. The base is what we are changing by our constant successive ratio. What are we multiplying by every hour to get the next value? Because remember that B is a factor, and factor means to multiply. So here I multiplied by 1/2 to get 2. I multiplied by 1/2 to get 1. I multiplied by 1/2 to get 1/2. I multiplied by 1/2 to get 1/4. So my function here is A of t is equal to 4, since 4 is my initial amount, times 1/2, that's our decay factor, raised to the t power. So in summary, our exponential function is f of x equals ab to the x, where a is my vertical intercept and b is the base of the exponential expression. If b is greater than 1, then the function is increasing and b is going to be the growth factor. If I have an increasing exponential function, this is the shape. So whether I'm at a base of 2 or a base of 100, all my exponential functions that are increasing are going to have this shape to them. If my base is between 0 and 1, I have a decay factor, and my function will be decreasing. So this will be the shape for my decreasing exponential functions. We notice that both of these different types of exponential functions have a horizontal asymptote at y equals 0, meaning that the function is never going to go below the x-axis. So that can be used to help us with our domain and our range. We notice that our graph of the exponential function, whether it's increasing or decreasing, has no breaks in it, meaning it has a nice smooth curve from negative infinity all the way to positive infinity. So that means my domain is going to run from negative infinity to positive infinity. However, because we can never go below the x-axis, our range is restricted that way. So my range is going to be all the values that are greater than 0. So we can write our domain as negative infinity to positive infinity, or all real numbers. And our range is going to be all positive real numbers, so from 0 to positive infinity.